So let's get started. Week 1, part 1. If you go to the learning path in the ebook, then you will see that the first part of week 1 consists of qualitative modeling. Although this course is about quantitative modeling, we make a lot of qualitative diagrams. First of all, to conceptualize problems, to conceptualize issues. Second, to elicit mental models from folks, especially in group settings, where we make group models that are joint, let's say, understandings of issues created by the people in the room. And third, we use them, and that's especially relevant for this course, to communicate the dominant feedback loops that cause a particular type of behavior and possibly the shift in dominance between different feedback loops. The types of diagrams that are most often used in system dynamics are causal loop diagrams, and in these diagrams you will see variables and arrows, and each of these arrows expresses a causal relation between these variables, the variables it connects. And this is very important. These relations are causal relations. Now, I open an older version of VenSim. You have a newer version. The only difference is, well, one of the differences is the way it looks interface-wise. But we are going to use exactly the same variables, but I'm not going to install a newer version on this one because it would mess up my scientific installation. Anyway, so as I said, we have variables. So I click on a variable button and I can add a variable to my program. I call it variable 1 and another variable. And then if I have a normal single arrow between them, then this actually expresses that variable 1 causes changes in variable 2. So if, for instance, variable 1 increases, and therefore because of that variable 2 increases too, then I would give this even a positive link polarity. So you see now we have a plus sign. If it's not clear here, then we can also put it at the handle. This basically means that if variable 1 increases beyond what it already was, then variable 2 will increase beyond its value as well. But it also means that if variable 1 goes down, then variable 2 actually goes down below what it already was. That's at least the simplistic explanation. A slightly more complicated explanation is written down in the ebook, and I will come back to that when we talk about stocks and flows. We can also have a different type of relation, namely a negative causal link between two variables. Variable 4, and if we have a negative link between two variables, which again I can label with a negative polarity sign, then this actually means that if variable 3, again, the simple version is that if variable 3 goes up, then variable 4 will actually go down. Or, yeah, if variable 3 goes down, then variable 4 goes up. Again, there's a slightly more complicated explanation, and I will get to that when we talk about stocks and flows. That is, different types of variables, because now we are just considering all these variables to be, well, let's say just variables. Well, whenever we have these causal links, and of course there's, in most models there won't be just a single causal link, but if they feed back, then we get feedback loops. That is to say, if variable 3 influences variable 4 and maybe a couple of others, but then in the end it feeds back on itself, then we have a feedback loop. Say this feedback loop is consists of a positive link here and a negative link, then this actually means that if variable 4 goes up, then variable 3 goes up beyond what it would have been, but then variable 4 will actually go down or increase less than what it would have been. So this basically means that we get a negative feedback loop. So I'm going to immediately indicate that here by saying this is a feedback loop that is negative, and this is pretty important information because it already tells us something about this feedback loop, its behavior in isolation. In isolation, it actually means that that this feedback loop will be showing convergent behavior, or as they also call it, goal-seeking behavior. I will come back to that when we make simulation models. And this is fundamentally different from a feedback loop that is positive, because if a feedback loop only consists of positive causal links or an even number of negative links, then this actually means that if variable 1 in this case goes up, variable 2 goes up beyond what it would have been without this influence, but then variable 1 goes up again beyond what it would have been. So this basically means that we get exponential increase in such cases in case of a positive feedback loop. No, it is actually clockwise. But it also means that if variable 1 goes down, then variable beyond what it would have been, then variable 2 actually goes down beyond what it would have been without this influence, and if variable 2 goes down, then variable 1 goes down even further, and so on. So you can also have not really exponential decrease. I will show that type of behavior when we actually get to simulation models as well. So this is really the core. Causal loop diagrams almost never consist of a single loop. It would be extremely exceptional, and there are always some exceptions. For instance, I told you that a positive feedback loop in isolation will show exponential increase or decrease, but that's not always the case. I'll come back to that as well. Now, in the first part, you really need to practice and learn how to use your simulation software. But it's also good to do the exercises and practice a little. Now, the type of exercises become much more difficult after a while here, but the simple ones are really good to get started with. So I suggest you really stick to the learning path for this first part, and we will get back to group model building and making proper conceptual models in the second 5-week period of this course. But this is just to get an introduction.